Hi, everyone. We are on our final chapter of the year. Isn't that wild? Like, I am just in shock. Just can't get over it how fast the year's gone. And we're ending on circles. I'm excited because I wasn't able to teach this last year because of COVID. We didn't get here, so I'm excited. I love circles. I love this unit. It's just something different, something, I don't know, it's just good. We don't talk about circles a lot, so I like how we get to end the year this way. A lot of this stuff today is going to be a bit of a review because we already talked about circumference before and area, and you kind of already know the basics of circles. So kind of just bear with me, but there is kind of some new terminology too. All right. But the whole idea of today is you're going to learn some properties of circles, and we're going to use these properties to solve problems about circles. Okay. So again, some of the stuff we already know, like a circle. But do you know the definition of a circle? The definition of a circle is the set of all points in a plane equidistant from a given point called the center. So here would be our center here, C, and all of these points on your circle are the same distance away from C. And how do we know that? Well, it's because they're all just one radii or radius away. All your radii in the circle are the same length. That's why they're equidistant. So that's fun. So you can name a circle in a few different ways. You could either say circle C, because you name it by its center, or you do a little circle with a dot in the center, C, circle C. Those mean the same thing. A radius, we know, is a segment with the endpoints at the center and one on the circle. So like CF could be an example. A few more on there would be DC, or the other one there, C. Those would all be radii. The order of those letters don't matter. You can flip the order and have FC or DC or CD and so on. A chord, this might be a new word for you, is a segment with both of its endpoints on the circle. So like AB, you guys see how both A and B are on the circle? So this guy right here is a chord. A chord. Same with DE. Both of the endpoints of that segment are on the circle, so it is a chord. And then lastly, we have a diameter, which now you can say is a more specific type of chord. So it's a chord that passes through the center. So a diameter has to go through your center. Otherwise, it's not a diameter. It would just be a chord. So DE is our only option on this example here. Okay, let's practice naming some of these things on a different example. Okay, let's see if we can maybe shrink this a bit. Just help us out. Okay, this should do. Name the circle. Remember, you name it by its center. So you could say circle N, or the circle with a dot in the center, N. A chord, you have some options here. Just remember two of them, both of their endpoints have to be on the edge of your circle. So like F, E, this would be a chord. That's one. Remember, a diameter has to be a chord that goes through the center. So our only option there is DF. And a radius, we have a few options here. Let's just do, should do CN. From the center to the edge of your circle. It's a terrible C. Okay, CN. Okay, now we're going to do a little bit of math. It says if CN is 8, so if our radius is 8, find DN. So what would my other radius be? Well, we know that all radii in a circle are congruent, so it would also be 8. And lastly, if EN, where is EN? So if EN is 13, find the diameter of the circle. So remember, your radius is half as long as your diameter. So 13 times 2 gives us 26 feet. I suppose you should probably label this. This is feet. This one was centimeters. Okay. Woohoo! Again, I don't think there's anything new there for you, but it's just a nice refresh. A good refresh. Okay, just some things to note here. Congruent circles. Two circles are considered congruent if they have congruent radii. So in this example here, if we were told that GH is congruent to JK, then our two circles would be congruent. Kind of obvious, right? I think we know that. Similar circles. It's kind of fun. All circles are similar. So if you have just any given circles, no matter what, they are similar because they're just only one thing to compare. They only have a radii, right? That's the only measurement they have. So if this was 4 and this was 2, they would be similar because you just have one thing to compare. There's nothing to compare your scale factor of a half to. There's just a half. I don't have a height here. I don't have another base. It's just one measurement. So no matter what, they're always similar. Concentric, this might be a new term for you, but concentric circles are coplanar, so they're on the same plane, and have the same center. So they're two circles that are basically laying in each other. So like you guys see here, both these circles have center at A. The smaller one has radius AB. And then our bigger circle has a radius of AC. But again, they both have the same center, so they're concentric. So a few more housekeeping things to note, kids. Our circles can intersect and look in different ways here. So you can either have your circles intersecting at 2 spots, and again, it can look a little bit different depending on what's happening in your diagram. One point of intersection, they just touch once. We'll eventually learn when things just touch once. It's called a tangent, a point of tangency. Tangent point. More to come later. Don't worry about that. It's later in the chapter. And then obviously you can have circles that don't touch at all. So they're just both off floating in space. Okay, it says the diameters of circle A. Well, this isn't helpful. I shrink this a bit. Here we go. Okay. So it says the diameters of circle A, B, and C are 8 inches, 18, and 11, respectively. Find each measure. Okay, so just to help my brain, I know that circle A, this has a radius, or diameter, excuse me, of 8. Circle B has a diameter of 18, and C has a diameter of 11. Beautiful. And our goal right now is to find FG. We are looking for this guy right here. That's what we're looking for. So you just kind of have to play around a little bit, right? So if I know that my diameter on circle A here is 8, my radius right here is 4. And then if we were told that our diameter of circle B is 18, what's left over of this whole thing if I take 4 away? So 18 minus 4 gives us what, you guys? 14? 14 inches? So from here to here is 14, because together 4 plus 14 gives us our 18. That was fun. Beautiful. Okay, let me erase that. Our next one we are looking for is FB. Now this little guy. So a similar process. We know that AF is half of 8, so 4. And we know that half of 18 would be 9. So we're looking for what's left over of 9 if we take 4 away. So 9 minus 4 gives us 5 inches. And check yourself. 4 plus 5 does indeed give us 9. Perfect. Hitting you with some more vocab. These seem to be confusing sometimes for us. So you're going to have inscribed versus circumscribed. So inscribed is a polygon in a circle if all of its vertices lie on the circle. So it's inside your circle. So like, look, kind of starts like inside. It's inside the circle, right? Inside, inscribed. So in this example here, quadrilateral LMNP is inscribed in our circle, right? All of my corners, all those vertices of this quadrilateral are on the outside or on the edge of our circle. So therefore it does mean it's inscribed. Okay. Circumscribed, a circle is circumscribed about a polygon if it contains all the vertices of a polygon. So really just the opposite of what we just said. So this circle is circumscribed around the polygon because it contains all of those vertices of that polygon. So circle K is circumscribed about quadrilateral LMNP. All right, so let's talk a little bit about examples of these words. It says a square with side length 9 is inscribed, so it's inside our circle here, circle J. Find the exact circumference of circle J. So remember circumference? 2 pi r. And we want exact, right? So that means no decimals. So this will be fun for us to review. No decimals. Okay. So we have a square, so we know that these angles here are 45. So what's nice, we have a 45, 45, 90 triangle. So I know this side right here would be 9. And then our hypotenuse. So to go from your leg to your hypotenuse, it's just 9 root 2. If you forgot your shortcut, you could have done Pythagorean theorem, but it's nice that we can rely on those shortcuts because it makes our life easier. Okay, so now if my diameter is 9 root 2, our radius would be half that, so 4.5 root 2. Okay, so now let's plug into our circumference. So circumference equals 2 pi. Our radius is 4.5 root 2. So now we simplify a bit here, kids. 2 times 4.5 is 9. And then since they want it exact, we don't do anything else. We leave it with the pi, we leave it with the radical, so this is it. 9 pi root 2, do we have units, inches? That's it. And one more to end our time together here on this video lesson. It says the right triangle shown is inscribed, so it's inside our circle D. Find the exact circumference of circle D, so same idea. Okay, this time, this could be a special right triangle, we just don't know. But since we don't have any angle measures other than we have this right angle here, we could do Pythagorean theorem to figure out what our hypotenuse, aka our diameter is. So 12 squared plus 8 squared equals x squared. 144 plus 64 x squared. 208 equals x squared. All right, this is going to kill some of you. We got to break it down. So if you forgot, we're thinking of what perfect squares. Forgot 36. Sorry, children. 36, 49, 64. Okay, that should be enough. Okay, which one of these evenly goes in here? Again, you want this trial and error. You just take 208 divided by 49. Oh, I get a decimal, not that one. 208 divided by 36. Oh, decimal, and so on. But because you're watching a video, I do know the answer. 16 goes in there 13 times. And we know the square root of 16 is 4 root 13. Okay, so that's our diameter. So our diameter equals 4 root 13, which means our radius is 2 root 13. Plug into our circumference. So 2 pi, our radius of 2 root 13. Now again, they want the exact answer. So 2 times 2 is 4 pi 13. Do we have units? Centimeters. And that's it. All right. Well, good work. So I'll see you tomorrow. Hope you had a great day. Hope you're having a great day. And I hope you continue to have a good day. Until then, be good. Wear your seatbelt. Live the tradition. Onward Central. Goodbye.